And I would also want people to interact within the talk by using the chat option, or maybe unmute themselves by raising their hand and asking the host, that is Vijay, to unmute them. And we'll have a kind of a very laid back talk. I would not want to impose information on you. I would rather want you to intuitively gather information from the talk, how so much you can. And if something does not make sense or something feels funny, please let me know. I would really want to convey whatever I can give it to you. And this topic, that is attention, is really very exciting for me. As you can see, like I'm coming out of my chair and kind of talking to you, and in a very hand baby gestures. So please let me know how you feel, what feels funny, and we can start from there. So I am Aritra. I am your speaker for today. So I'm a deep learning associate at pymetsearch.com, and I learned with a learning rate of 1 in 10. That means I learn very slowly. So please don't get overwhelmed with the content that I'm providing you today. Learn slowly, gather things in your own pace, and we'll take it from there. I'm also an active contributor to Keras.io, and I specialize in computer vision. So my day job mostly includes me breaking down complicated research papers and providing code walkthroughs. So let's get started. The first thing that I would want you all to understand is how we can visualize MLPs. MLP stands for multi-layer perceptrons. And the first question that I would want to ask to all of you is, what is the first thing that comes to your mind when I talk about MLPs? MLPs means weights and biases, right? That's about it. So you have an input, which is X, and you multiply weights with X and add some kind of biases, right? Now with weights and biases, you form a kind of non-linearity on top of it. You wrap the weights and biases with some non-linearity, and that squishes and squashes the whole dimension layer, and you find things to represent themselves better. Like the input, I'm kind of modeling on the input. Now, why did I name the slide Visualize MLP? I wanted you all to understand that MLPs have a very basic inherent implicit property, that is it models on the inputs individually. This is going to lay a foundation of my entire slide deck. So please keep in mind that MLPs model on inputs individually. So as you can see here, that X1, X2, X3, to Xn, each of them go in individually, get models individually, and the representation that I kind of learned from the MLP is an individual one-to-one mapping, right? This forms a huge role in the whole slide deck. So I just want you all to imbibe the whole essence. Now, due to the fact that I'm talking about attention or transformers in the latest slide, so I just wanted you all to know why I am talking about sequential data. So in the first slide, we understood about MLPs. So MLPs are basically weights, biases, non-linearities, squishing and squashing of the dimensions, representation of the inputs. Now, what is a sequential data? Sequential data is not only the tokens or individual inputs, it's also about the way the tokens are placed. That means if I say I am a good boy, that means the tokens I am a good boy, these are all the individual tokens. These are X1, X2, X3, X4 to Xn, that those go into the MLP as shown in the previous slide. And also the placement that they are in, like I is placed right before am a good boy. The placement matters a lot. So in a sequential data, the sequence matters, that is the order matters. Now let's go to an example where this order really matters. I think this slide is self-explanatory, so I'll move on. Now let's talk about a problem of MLPs. Let's say I give you the task of modeling the sequential data with a model, and you have nothing else but MLPs. So you say, okay, Aritra, I'll just feed in my sequential data to the MLPs and see where it takes me. Now think about it. Each of the tokens, that is X1, X2, X3, X4, X5, that is I am a good boy, gets modeled individually by an MLP, right? So I gets represented in a manner, am gets represented in a manner, good boy gets represented in a manner. But does the MLP really know which word gets placed after which word, or does it know about the sequence of the entire sentence? It does not. Hence, this is where MLPs break uh, due to the fact that the task is a little different. And how do we do this? Like I am proposing a problem to you, and I am also going to give you a solution to this. So in comes RNN. What does RNN mean? RNN means recurrent neural networks. So we knew about, and so one thing about me is that I like going back and then coming forward to my slides, so that I always give you the essence of what we covered, so that it forms a very cool kind of evolution map in your heads. So what we learned in the previous slides is one, MLPs. What are MLPs? And how does MLP break? Like, how do I break my MLPs by giving it a bunch of words which have a sequence, but the MLPs can't figure out the sequence? So the RNN formula is kind of very similar to the MLP. So MLP is a function of X, which is the input. X is the input. It works on weights and biases. And now what the researchers did is that they introduced a hidden state vector. What does it do, or what does it depend on? It depends on the current input, right? X of t. And I'll make sure what this t is, or make you understand what this t is a little later. Just stick with me. So ht is a function which depends on x of t, that is the present input, and it also depends on something called ht minus 1. And this h and this h are the same thing, but it just so happens is that t is my time step. So if t is equal to 1, that means x of t is also equals to 1. So the current hidden state depends on the present input or current input, as well as on the past hidden state, right? This is the entire thing that recurrence neural networks is basically based on. So what did I cover? I covered MLPs, I covered sequential data, and now RNNs kind of magically want to model the entire sequence, because they not only cover the present input but also the past inputs. And when I want to cover the past inputs, or the model the past inputs, what I'm trying to do is I'm trying to also model the sequence of the data. If I am a good boy is given in to an RNN, it also knows where these words are, which was previously not possible with MLPs, right? So something like this happens. I'll let you all understand what the animation does, and we can later take up questions. So the first input goes in, I form a hidden loop, the hidden states get in, and it goes on. But this is a little daunting at this moment. So what I did is unfold them and kind of make you all understand what RNNs really stand for. So say, for example, I have X1, this is the first word that gets in, and I have a hidden state which also gets in. And this L1 is my RNN model, right? Now with this hidden state that goes in, and as you can see that the current state is X1 and the hidden state is H0. That means it can't see the slide deck. Is my slide deck not visible, Vijay?
This can confirm. I can see.
Okay. Others, could you please confirm that whether my slide deck is visible or not?
Yeah, it's visible.
Cool, cool. So what I was trying to convey is that with the current input, that is X1, I need a dependence on the past hidden state, that is H of 0, right? And both of them, when get in, I kind of build another hidden state, which is the current hidden state. So I'm using past and current a lot of times. Please feel free to ask questions where this current comes in. I just want you all to understand this subscript, and that will make your life easier when you are learning about RNN. So look at the subscript, you will be able to understand which time step am I talking about. So if the time step is 1, that is the current time step is 1, I want to model my hidden state, past hidden state, that is h of 0, to build a hidden state, which is h of 1, which is also called as the current hidden state. Now, what happens in this block propagates to the second block. Now, in the second block, my time step shifts to time t is equals to 2. And when I do a t is equals to 2, I kind of model the h1 as well as x of 2 to build another hidden state, which is h of 2. Now think about it. At x of 5, that is the last time step of my entire sequence, I'm not only doing a dependence kind of injection to h of 4 as well as x of 5, but I'm also very sure about the entire sequence. Am I not right? Because h of 4 depends on h of 3, h of 3 depends on h of 2, h of 2 depends on h of 1, and h of 1 depends on h of 0. This is where recurrence is. The recurrence formula itself tells you that you have got to go back in time and let the whole model depend on the entire sequence. And hypothetically, and I stress on the word hypothetically, it should model the entire sequence, right? And I would like you all to please interact with me. So the question is RNNs and the interaction of RNNs with the past sequence a little clear or intuitive enough for me to go ahead? Because this also forms like a basic intuition, which we will later build upon attention. So I would look at the chats now.
Yeah, if you have any question, you can unmute yourself and ask the question as well.
Mm-hmm. Cool. I don't seem to have any questions. I'll move on. Now, right after RNNs, the thing I like to do most with it's my personal opinion, is that I like to build an intuition and break it as soon as I build the intuition, so that you all kind of understand the curiosity that I go in with, like doing research or kind of breaking the papers. So the first one was MLPs. I kind of told you where MLPs break. Then there was RNNs, and I'm now going to tell you where RNNs are going to break. Now the problems with RNN is that the tan H nonlinearity has a derivative which is tan H bar. I'm not going to get into too much of details, but if this is tan H, the red graph is tan H, and this is the tan H bar or the derivative of tan H, right? So I'm just going to showcase some of the graphs, and we'll kind of know where my RNNs are going to fail, right? And I am assuming that people here understand what backpropagation is and how do we optimize a neural network algorithm. So I just go to a whiteboard and quickly draw a little thing. So it's a 2D kind of graph where my x-axis are the weights and my y-axis are the loss. So most of the books that we kind of covered in deep learning or the intuitions that we build are something like this, right? So with weights, there is a dependence of the loss. And we try to optimize the weights so that my loss gets to a minimum. Am I not correct? Now, to do that, to optimize that, what we try to do is we try to build the gradients of my loss with respect to my weights, right? And how do we do that? We do simple chain rule, which we learn in class 11 and 12 in our basic calculus classes. And we do a simple chain rule, and we try to understand what the gradients are of the loss with respect to the weights. And we try to optimize the parameters with an optimizer, say, for example, a stochastic gradient descent or an RMS prop or an ADAM or something like that, right? And I don't want you all to get very scared with the notations. Hence, I squished the entire notation with a product formulation. Why do we have so many products, you may ask? We have so many products because with the chain rule and the recurrence formula of an RNN, what basically happens is with the derivative of loss with respect to the last hidden state, the last hidden state in turn depends on the previous hidden state, the previous hidden state depends on the previous hidden state, and so on. Hence, there is a lot of product terms in the chain rule itself, right? So we covered the loss. We want to now have the gradients of the loss with respect to the weights, and there are a lot of product terms inside of the loss because of the chain rule. These are the three main things. I don't want you all to start scribbling the mathematical notations. I just want you all to understand where this product notation comes in. And now, with the loss in mind, with the gradient in mind, and with the product term in mind, I'm just going to update the gradient formulation of the tan H inside it, and we have something called this. It's basically the same thing where del of H with respect to the previous state is kind of substituted with this entire equation, right? So please stay with me. This is the slide where it gets interesting. Okay, so we start with tan H of X, which is Fx. So tan H of X is the red graph. We then go to the derivative of tan H of X, which is this blue graph. And now we have something called the derivative times A. That means we are trying to do a product of this derivative A times. So tan H bar X times A. That means we are going to product it A times. And this is really intuitive. So A, when A is 1, I have one product. When A is 2, I have two products. When A is 3, it has three products. But when I turn on the slider, can you see something really interesting happening? When A is 98 and 100, it really squishes to the 0 part. I started off with the x-axis of -3 to 3. And now I am going to end really close to 0. Now, can somebody answer as to why I don't want this behavior? I'll give you some time. Yep, that's right. So as soon as we go into the into the areas where the gradients are really close to 0, that is where I understand that my gradients are going to vanish. It does not even matter. Like if I tell you I have my gradients equal to 0, my optimizer that takes care of these gradients and optimizes my weights are going to say that, oh, it's working fine. You don't have a gradient. It's already in minima. I'm not going to optimize anything. And that's a problem because I have a loss. The gradients are 0. That does not mean that I have a perfectly optimized model. I need to still understand the gradients which are back propagating. But in RNNs, with the product term being so huge, the gradients somehow vanish in the middle of the sequence. So remember how I used the term hypothetically, because RNNs hypothetically should model the entire sequence. But due to the fact that there are a lot of sequences and a lot of products in the calculus itself of gradients, it kind of goes to 0 and the gradients vanish. So that's going to be a problem. So let's talk about an upgrade. So MLP sequential data, not working with MLPs, going to RNNs, not working with RNNs. Now what's this? Now what's the solution, Aritra? I know that RNNs should have worked, but it certainly did not. What researchers did, and to mention, Jürgen Schmidhuber did, and this is a dated paper. LSTMs are a dated paper. If I'm not right, it's a paper from '94. So I tip my hat to Jürgen Schmidhuber and team for do RNNs also have exploding gradients problem? It should because with products, what happens is, okay, so the question was, do RNNs have a vanishing as well as a exploding gradient problem? So with a negative term inside of the products and a one by reciprocal term as gradients, it should go to infinity. But I haven't, in my research terms, haven't seen exploding gradients. So that's a good question. If you get to see in exploding gradients in your Keras model or PyTorch model or whatever, please let me know. But hypothetically, it should. And it is more, it's more lenient to get a vanishing gradient than a exploding gradient. And for people who don't understand exploding gradient, it's just the reverse of vanishing gradient. Vanishing gradient is where the gradients go to zero, and exploding gradient is where the gradients go to infinity. Both are very harmful for the model, because in vanishing gradients the model does not, like, the optimizer does not optimize at all, because it kind of knows that the gradients are zero. And with exploding gradients, the optimizer goes berserk over the entire suite of gradients. If something goes to infinity, I'm not going to tune the model. I will not be able to tune the model. So that's a good question. Now, going back to my slides, an upgrade is an LSTM, and Jürgen Schmidhuber and team in '94 kind of laid a foundation of how to kind of break this vanishing gradient problem. What they did, and it's highlighted in blue, is they provided a highway network. So the analogy being that, say for example, you are driving on a road and you have a lot of traffic. And you won't be able to reach the destination quite on the time. And you see a bridge or a highway which has free pass and there's no traffic at all. You take the highway network and you go to you go to your destination, or you reach the destination in time. What Schmidhuber did is that with the same architecture of RNNs and with a gating mechanism, I'm not going too much in details of LSTMs right now. I'm just going to make you all understand that in this parallel sequence or the highway network, there are no nonlinearities to account for, and there is no product term to account for. So the gradients don't really need to, it's very unintuitive if they go to vanishing gradients or if they explode their gradients. So they just go to this highway network and they pass as they should be. It just is matrix addition and matrix multiplication, which is great for a model. Once you include a nonlinearity like tanh or a derivative of tanh, it's going to, or a sigma or a softmax or whatever, it's going to suppress the gradients. Now with the highway network, that does not happen. And again, the term hypothetically LSTMs should represent the entire gradients and also represent the entire sequence. But due to this representation bottleneck, even LSTMs do not have the capacity to model a paragraph of text. So even LSTMs have this problem with a larger sequence than RNNs. And you would be able to figure it out yourself when you are trying to model an RNN sequence on, say, 50 words, and an LSTM sequence on maybe 500 words or 1,000 words. But even LSTMs have this vanishing gradient problem. Now let's take a step back. I'm going to give you a minute to ponder upon what are the things that I wanted you all to have a basic foundation on. And I'm going to check out the chat real soon so that I know that I haven't missed any question. So the first thing was MLPs. I broke MLPs, understood about sequential data. I understood RNNs. I also broke RNNs and then went to LSTMs. And I think vanishing gradients, or the intuition behind vanishing gradients, is a little clear. So I'll check the chat real quick. Yeah, that's a really good point, Ramesh. So Ramesh says that you can clip the values of the gradients so that it does not overflow to infinities. And this is something which we often do with generative adversarial networks or GANs, and for that matter, variational autoencoders. So we try to stop gradient or clip the gradient so that it does not overflow. But in my opinion, I would not want to stop or clip the gradients because it kind of has this sphere in which the distribution is bounded in. So if I can have another architecture which probably deals with this vanishing gradient or exploding gradient, I would choose that over stopping gradients or clipping gradients. But if I don't have an architecture, this is the way to go. Bidirectional LSTMs address the problem of LSTMs to some extent. Absolutely right. So what do you mean by bidirectional LSTMs is that LSTMs or RNNs, as I have shown in the deck is one way, like I am a good boy. It goes left to right. But bidirectional LSTMs are a little tricky and they go both ways. So it's bidirectional. I am a good boy and the reversed sentence, both of them are kind of learning on the same with the same end-to-end model. So that kind of deals with the vanishing gradient problem. But another question is that if you have a sentence of or a paragraph of 1,000 text and your LSTM is only capable of modeling the first 5 words, it's not going to help. So that does solve to some extent, but not quite. Let's move on to attention. That is the main topic of this whole talk. With attention, what I'm trying to give you all the essence of is not the whole math behind attention. It's more of why we have chosen attention. What is it that really calls to us to get into attention? I am a good boy has a positive connotation to it because of the word good, right? And this word is something which I would want to attend to, or when I'm saying that I really did not like a movie. What are the words that we are attending to? Am I attending to the whole sequence or am I attending to words? With that question, let's move ahead. So take a deep breath because this is going to be a long slide. We start off with the basic RNN architecture. So you had me at attention is the input sequence and we feed that into the RNN. And what we do is we kind of give an auxiliary network. And by auxiliary, what I mean is a network which is not part of the RNN. It's disjoint to the RNN and an auxiliary network which learns where in the sentence I need to attend to. So please pay attention in this slide and stick with me. So you had me at attention is the input. I give it to the RNNs, and the last state or the last hidden state, that is h of t, remember, h of t models on the entire sentence. So h of t is the representation of the entire sentence you had me at attention. Why? Because again, we are doing recurrence neural networks, and due to the recurrence formula, h of t depends on h of t minus 1, which in turn depends on h of t minus 2, t minus 3, to h of 0, right? So that goes into a multi-layer perceptron. Now, with the multi-layer perceptron, we are basically trying to project my entire representation that I learned from this input into some other latent dimension. You can omit the MLP, but we give an MLP to learn a different flavor of the representation. And the flavor of the representation is called a query. Now, let me ask you, what do you mean by query? Query is something which we want to query, right? Like if there is a word I want to query in dictionary, I would like to look for that. I would like to look for that word. I would like to look for the meaning or something like that. So think of queries as something which I'm searching for. And the query goes into every other hidden state that the RNN has made. So remember, if U goes into the RNN builds a hidden state. That is the first hidden state. Had builds the second hidden state. Me at attention builds individual hidden states. And this query kind of goes and tries to figure out which hidden state in the entire input sequence is very important for my query. So it's like going to the dictionary and kind of attending to which page might have that word. So which, if I'm searching for a word called boy, I'm not going to go to G or Z. I'm going to go to A, C, B, and then going into O and then Y, right? So I'm trying to attend my query with all the hidden states that are there with my RNNs. And here for the sake of simplicity, I did not build another MLP, but what happens is that with each of the hidden state that goes out of the RNN, there is a small MLP which does not have a nonlinearity. It just projects the current hidden state or the hidden state that I'm working on to a key. And what do we mean by key? A key is something which the query tries to bring similarity to or tries to attend to. So a query comes out and it tries to attend to each and every individual key. Now, once we have all the keys and queries, we parse them, we concat them together, and we pass them through an MLP to again project it. You can omit the MLPs. It's just for the sake of your understanding that I'm trying to, map one query to each and every individual key. So there are 5 keys here: key 1, key 2, key 3, key 4, and key 5. And these in turn, when sent into a softmax or a softmax layer, it gives the probability distribution, as you can see in red, a probability distribution of which query is intensely needed to which keys, right? Does that make sense, or should I go back a step and kind of make sense of the entire situation? Because I think it's a little, I need to go a little slow. And if you all are comfortable with it, I can move ahead. If you're not, I'll just go back and kind of rewind and speak again. So I'll be seeing the chat now. Okay. So the problem here is that with the hidden state representation that goes into the RNNs, we have a query, and each of the query is trying to attend to each of the key there, or one query is trying to attend to each of the key that comes out of the RNNs. And this RNN key that is getting attended to one query is going into a softmax just because I want a probability distribution out of it. Why do we want a probability distribution, you may ask? The probability distribution basically tells you how much probable is a key in terms of the query. So take like in this diagram itself, key 3 plays a vital information in the query making. Key 3 is very important for whatever I'm going to do ahead. Key 2 is relatively smaller in intensity, or is not that important, but is still important. And key 4, key 5, and key 1 are not that important at all, right? In terms of the query and key matching. So the query goes in, the keys come out, and with each query and key pair, I am trying to figure out which of my key is going to make a lot of sense when I pass them to the other layers. So it's kind of a probability distribution of which is important and which is not. And by importance, can you kind of bridge the gap between importance and attention? Like I told you, I did not like the movie has a negative connotation to it. And did not like are the 3 words which kind of build the sentiment of a negative connotation. And here you had me at attention and the query coming out. With the softmax probability distribution, I can safely say that key 3 or me and had have a bigger intensity or importance, or I need to attend to them more, right? So that is the work of softmax. The softmax basically does that. Now there is this intuition that I would want you all to build, is that with the softmax I get what to attend to, but do I get how much does one thing should, like how much should our vector representation or maybe a word should be attended to? I need to multiply this probability with this key, or say the hidden state of key 3, so that I get a scaled version of V3. So say, for example, key 3 has a hidden representation of h of 3. And this h of 3 gets multiplied with the softmax probability, and this softmax probability is 0.9. So I'm essentially scaling how much intense is my vector representation of H3, and that is the blue connotation. I'll just read the chat real quick. So Ayush here says that is the key H of I, which is hidden state of RNN, or is key a projected hidden state of the MLP? Yes, that is correct. Can we say that the query is the hidden representation of the entire sequence, while the keys are the hidden representation of individual tokens? Absolutely right. So the queries form the hidden representation of the entire sequence you had me at attention, and the keys are hidden state representation or projection of the hidden state representation of individual words that I'm going to attend to. Now moving back, after having the probability distribution, if I scale my hidden representation, I'm going to get a vector representation of each and individual word. And I'm also going to understand which word needs to be intensely attended to and which words can be neglected. So attention not only means that I need to attend to something, it also means it's counterintuitive, but it also means that I'm not going to attend to something. I'm going to neglect them, right? So value 4, value 5, value 1 are neglected, and while value 2 and value 3 are attended to. Now, right after I have such a great, rich information of my entire sequence, I'm going to concatenate the entire thing and pass it to my classification head along with my query, right? The query goes into the classification head, and the concatenated version of the attention kind of module goes into the attention head, classification head as well. What does it do, Aritra? The main motivation here is that with RNNs, there was a bottleneck. Like I could not, due to the vanishing gradient problem, I could not module you had me at attention properly. But now with the attention head on top of my RNNs, I'm not only able to module the entire sequence, but I'm also able to quantify the information of which words should be attended to and which words should be neglected, so that my model can attend to places and can neglect places, right? So that was the entire slide. I would like you all to take a minute and imbibe this in, and I'll be taking questions. So looking at the chat right now, I'll have some water too. So as far as I would like to know from you all is that am I going too quick or am I going too slow? Is attention a little intuitive, if not the entire thing? Is a little intuitive to how we are kind of using the softmax? Why are we using a softmax in the first place? Why not a sigmoid? And why are we doing a kind of scaling the probability distribution with the values? So I still have no one entered anything. I don't see queries, so I'll just move ahead. Now, let's go to the main crux of the entire slide, which is transformers. Let's face it, we are here for transformers, and this guy is blabbering things from a long time, and it's not coming to transformers at all. So here you are. In 2017, there was this millennial paper, if not true, millennial paper by Ashish Vaswani et al. From the Google Brain team, and that basically defines whatever we are doing in the world of natural language processing. That is transformers. Now, right after we understand what attention is, how attention is really involved, and how do we attend to things, we come to the transformers architecture. Now, there are a lot of caveats which I am going to miss because of the lack of time constraints. So I'm going to quickly cover them, and if you have any concerns, please let me know in the Q&A section, which happens later. The first things first, as far as I did in the slides, it was more of like an encoder architecture where I'm just giving an input of words and I'm trying to encode the entire thing into a hidden state, right? And I'm also going to attend to the inputs at places where I need, and I'm also going to neglect them. But Vaswani et al., or the attention is all you need paper, they suggest a task which is called as a sequence to sequence task, which means that you have an encoder, you also have a decoder. And due to the fact that I'm Bengali, I'm going to use an example where I'm trying to uh, module English to Bengali, which is a sequence to sequence problem. So if I say I am a good boy, that forms the English part, and in Bengali, ami ekta bhalo chele, ba ami bhalo chele is the Bengali equivalent of I am a good boy, right? And a sequence to sequence model, a hypothetically perfectly trained sequence to sequence model will, map each sentence's information and bridge the gap between the two dialects or two languages. So with transformers, what we have is two columns, and and in this slide, I'm going to build an intuition of how to read the architecture. It's not how to dive deep into the architecture. It's more or like how to read the architecture so that when you go to this paper, it becomes easier for you. So we feed in inputs, and remember the inputs are in English and the outputs are in Bengali. So inputs get in. I do an input embedding. So what do we mean by input embedding? The input embedding is a simple kind of formula or a function that maps each and every input to a different or projects each and every input to a different representation dimension or a latent dimension, as we say it. So with input embedding, we also have something called a positional embedding. I'm going to cover this block real quick and then going to make sense of what positional encoding is. So inputs, input embedding, we add positional embedding to it. I'm sorry, did I miss something? Okay. So I add positional embeddings to the input embeddings. And then I do something called as a multi-head attention. I add and normalize the outputs. I also add a residual connection to it. Then add a feed-forward network, add normalize them, and also add a residual network to it. So in my later slides, I will cover mostly what multi-head attention, cross, and self mean. So what the encoder essentially does, as you might have known in an auto encoder kind of a situation where you input an image and the image is encoded to a different latent dimension, the same thing happens. So I am a good boy, the sentence gets encoded and represented. That is, the entire sentence gets represented into a single vector, which is highly rich in information. That is the task of an encoder. And a decoder, that gets Bengali inputs of the same meaning as that of the English inputs, gets decoded, as in the English representation flows in, the Bengali inputs get in, both of them bridge the gap, tries to figure out what information it holds, and then in an output, I try to figure out the Bengali equivalent of the encoded input. So that is how a sequence to sequence model works. And what basically took deep learning by storm is that in this entire architecture, we will not find anything but multi-head attentions and feed-forward networks, which are basically known as multi-layer perceptrons, which we covered in the first slide. So they propose that attention is eventually all you need. Attention mechanism or the module attention is exactly what you need, and you can have like brilliant SOTA papers or models and you can deploy it everywhere. Now coming back to a little caveat that I missed is that positional encoding. So say for example, you have a sentence called I am a good boy. And what did MLPs do? It modeled on each word. What did RNNs do? It modeled on each word. It also knew where the sequence is, how the sequence is. Now, a little counterintuitive problem or fact of transformers or multi-head attention is that it is it does not know where the sequence is. I hate to break it to you, but it does not know where the sequence is, and it's very counterintuitive. Why do they work so well if they don't know how to model sequential data? That is where positional encodings come in. So say, for example, you have the same sentence. I'm going to repeat it over and over again so that you believe that I am a good boy. So with the same inputs, I am a good boy. I try to inject some information into my words so that those informations form those information form the intuition of where the words are. So attention is very bad with where the words are. Like the multi-head attention that I'm going to cover, they are very bad with where the words are. But as soon as you add or inject some positional information to it, attention seems to be working quite well, because it attends to words, but it also now knows where these words are going to be placed. So I am a good boy and some jumbled form of the word are going to have two different attention matrices or attention weights that are going to work. So the positional encoding is one of the best things that you will go on to read in the paper Attention Is All You Need by Goswami et al. Right? And in the next slide, like this, in this slide, the first thing that I am going to cover is the cross attention formulation. So cross attention basically means that you have queries, you have keys, and you have values, as shown in this slide, where you have queries, you have keys. So just a recap: queries are the representation of the entire sentence. Keys are representation of each word, and I'm trying to figure out which key is very important to my queries. And this query and key forms the attention weights or the probability score, like how much should I attend to. And the values that are scaled give you how much the value should be attended to, right? So it breaks down to three simple things: queries, keys, and values. Similarly, queries, keys, and values. And in the previous slide, I used an MLP to conjoin the queries and keys and try to figure out how much similar they are. But Vaswani et al. Said that Q and K can be simply dot producted. And with the dot product, you are essentially trying to figure out how similar the query is to the key. And with similarity, it intuitively builds that this query is similar to this key. Hence, this key is going to mean something to the query. This query, when goes into a classification head or a task, is going to attend to this key very much. And some dot products, when goes to 0, it means that this query should not be attended to this key, right? And with this root over dk, that is the dimension of the keys, I scale the qk. And I see a question: is the scale to get the value a learnable parameter? I don't think it's a learnable parameter. The problem that happens is that with the softmax formulation, a softmax gives you a softmax. Like, it gives you a probability distribution which has some parts peaked and the other parts relatively smaller. And with qk, or a big number, or a big dot product of matrices, you will find that when you do a softmax, it gives you one peak, like it goes to 0.9, and every other value is very close to 0, which is a problem, because I don't want to attend to one single word, right? I want to attend to a bunch of words, or maybe the entire sentence, if that makes sense. So when I do a normalization with the dk term, it quickly gives me a continuous distribution of the probability that we get out of softmax. So what I'm going to do is I'm going to add a collab notebook to my published deck on my Twitter handle. So if you all want to play with that, you're most welcome to. The collab notebook will have nothing but some statistics and some matplotlib plots, where you see that with qk, you have a standard deviation and a variance very small so that it gives a softmax distribution of a peak and everything goes to zero. But as soon as you do a normalization with the root over dk term, it gives you a very smooth softmax, which is very important, but it does not, so the problem is solved, but it does not give you a wrong notion of attention. It does not tell you that this word needs to get attended to if it is if it should be neglected. It does not give you wrong information, it just gives you a better representation of the entire attention formulation. So once this cross attention formulation becomes easy, we can move to the next slide. So a little thing that I also want to add on is that the key and the value comes from the input and the query comes from the output. So going to the previous slide, the inputs have the key and the values, but the outputs provide you with the queries, right? That is a cross attention. Hence, due to the fact that we have inputs as well as outputs, hence the name cross attention. Excuse me. Now, the question comes to a point where what happens if we do not have any output? What happens if we try to figure out the queries, the keys, and the values from the same input? That is where self-attention comes in. And self-attention is very analogous to self-realization. You attend to your own thoughts. You don't attend to somebody else's thoughts. And that is very philosophical, but that indeed helps transformers learn a lot better. So once you have I am a good boy, which is the input or the English input, and you kind of build a self-attention on it, when it gets trained with the loss and the backpropagation and all that stuff, it tries to figure out where in the word it should attend to itself. It is kind of building a representation of its own self, and which makes a lot of sense, because the input I am a good boy, when attended to itself, tries to figure out what should be the words or what should be the words I should be attending to, and providing those representations to the output so that the output gets a lot richer information. So it's kind of figuring out its own self in a very naive way, right? So with cross attention, self attention does not have a formulation difference. It's just the matter of source, like the queries, keys, and values come from the same input. The purpose of self-attention is to build better representation of self, right? Now let's come to, due to the fact that I'm from the computer vision community, I was excited when I read the paper of how attention is really important, how MLP is taking, like the transformer architecture is taken by storm and all that stuff. And I really wanted a paper to come out which harnessed these probabilities, which harnessed these possibilities of overcoming a lot of things. So let me ask you the question, how to translate our knowledge into the visual domain. And I'm going to give you some time on that, because this is really intuitive, and people who have read the next paper and know what I'm talking about, you're free to answer as well. How do I translate our entire knowledge of transformers into the visual domain? Yep. So we start with vision transformers. And what happens in vision transformers is that the images that I have, the image is not a sequential data, right? Words or sentences or time series data or anything that has an order is a sequential data. But now with vision transformers, we are essentially trying to figure out a way that use transformers, that use self-attention, that use multi-headed self-attention and all that stuff. But I really need to first figure out how I am going to represent my images as a sequence of data. So in the animation gave away. So the animation basically talks about patchifying and then ordering. And now when you order the data, it's basically forming a sequence of patches, and this sequence is the basis of how you are going to model your image, right? There are four sequences of the lovely dog picture, and that is all that is to vision transformers. You have transformers, you take the transformer architecture, and you have images. You patchify the images, you sequence them in an order, and then you send the patchification of like the patches into the transformers, and that's going to take care of everything. So there are, as we have also covered the transformers architecture. I'm not going to go through the transformer encoder. It's basically the same thing, and this is by Dosovitsky et al. It's a paper by Google team with ETH Zurich on the. If I'm not sure, it's published in 2020 on iClear. And the fascinating thing about vision transformers is that they did nothing else but used images as sequences and used a transformer. And they have vehemently told that we are not using a SOTA architecture. We are just genius people at Google who knew how to model that. And I'm going to also let you guys know that when you're doing research, it's not about the SOTA architectures which you should be after. You should also understand that there are a lot of possibilities which you can have with existing architectures. You just have to have a different perspective. And vision transformers is very close to my heart because they provide a different perspective to the problem. Now, with patchification, I have the sequences. Now there is a basic problem. Can somebody know, like, tell me what problem should I be facing when I have patches of images versus words? Uh, I'll look at the chat. Like, my question is, if I have words which goes into encoder, which goes into the transformer encoder, and if I have patches of images which goes into the transformer encoder, what is the one biggest problem that I should have? I'll take that answer, but it comes later. So Ayush rightly mentions that the problem is which positional embedding or which position. Okay, so I think there is. Vijay, could you let the person speak?
Yeah, they can unmute and talk.
Okay, yeah, go ahead, please. Order of the patch is not clear. Yeah, so it's kind of the same foundation that Ayush said. So that is not the biggest problem, and I'm really happy that you guys are kind of enjoying the thought process of the Google Brain team, right? This must be a blocker for them. They have images, they patched the images, they did a sequence, and they have a really big blocker. What is the blocker? Pixel, which is 2D or 1D. That's a good point. So when you have words, you embed them into a 1D, one dimension latent space. So if you have I am a good boy, you have I, which gets embedded to a vector. Am gets embedded to a vector, which is a 1D data. But in patches, that is a 3D data, which is kind of like 16, 16, 3, where 16 is the height, 16 is the width, and 3 is the channels or the dimension of the channels which it holds. But and why did I use 16 cross 16 is because the name of the paper is 16 cross 16 images are larger than words or something like that. So they patchify each of the patches in 16 height and width. But that's not the problem. I give you some other time, like a little bit more time. What should be the problem? What did Google do which we can't? We should. What is the problem? So I'm again repeating. I have images. I patched them, sequentially provided them. Just after that, I'm not able to do something which words do very quickly. Relationship between patches. Relationship between patches comes in a lot later when you, whatever the blocker is, you overcome the blocker, you pass it into the transformer encoder, and that relation between the patches forms inside the transformer encoder because of the attention mechanism. But that's not a problem. It's a very naive problem that you need to think of. I'll give you 2 more minutes, and then I'll start with the slides. Vectorize. Vectorize images. Could you elaborate? Because that's very close to the problem. Very close to the problem. You can unmute yourself and talk. It's not a problem, at least for me. Vectorize, and if you could elaborate.
Like it's easy to vectorize words than images.
Right. So the problem stems from that, but hear me out. So if you have words, the first thing that we do is we form a vocabulary of words, right? The vocabulary of words tends to be a dictionary which has the entire word, like all the unique words that are there that I'm going to model on. So if I say I am a good boy, hence it will form a dictionary of I am a good boy, and each of the words will have an index related to it, so that I can sample the embeddings which I form later. Now the problem here is that with image patches, no image patch is unique. I can just go on with my camera. I can have like different image, like the same image from different angles. And say, for example, the first patch is unique. The second patch might not be unique. But in words, if I form a vocabulary of words, I can understand that this word is unique. This word will be unique for the entire training sequence, right? So how do you form that vocabulary inside of the vision transformers? And then we stem to the vectorization problem, which was very nicely put out by one of my audience. So the problem first is that we can't vocabularize them. The second problem, which stems from vocabulary formation, is the vectorization problem. So how do we do that? What they did in Google Brain is that they're saying, okay, I don't need to vectorize them. Why do I need vocabulary? I don't need vocabulary. I'm not going to sample image patches. What I'm going to do is I'm going to linearly project each of the patches so that I have a different latent dimension. That is all. I don't need vocabulary. I'm just going to vectorize them. And this vectorization, the vectorization scheme is the linear projection of the flattened patches. What do you mean by linear projection? You just have a dense layer. You have all the patches. You pass the patches through a dense layer, and you have your tokens built. And these tokens, mind you, can be resized into a one-dimensional vector. And I think the problem that Ayush had previously sent in, that which token size should I do? Is it 2D? Is it 3D? Is it 1D? I am doing 1D, but I'm just going to have the patches, project them linearly without any activation, and going to resize them, right? So that basically it was the blocker. That was for me, it was a genius idea. And we are done with the blocker. And now once we are done with the blocker, and I'm not going to cover, for this moment, you can just look at the diagram from 1 to n. I'll cover 0 a little later. So 1 to n are the image patches which are vectorized in 1D. And now when the vectorized image patches get into the transformer encoder, the transformer does its magic. It gives global attention, it gives local attention, all that stuff happens. And at the very end, it gives you one vector which represents the entire image, right? It gives you the entire image representation. And one thing which I missed is that the patch embeddings, like after the patches are linearly projected, I also need to add positional embeddings, which was very important for transformers as well. And this positional embeddings is the same as that of transformers. So you're injecting some information into the tokens, which makes sense. Now, why did I not cover this? This is called as a class embedding. What does it do? It's a learnable parameter which kind of represents the entire image patches inside of the transformer encoder, so that at the end I'm getting only one vector. This is the vector that gets learned through the entire encoder, and this vector, that is a class embedding, extra learnable class embedding vector, goes to my MLP head or my object detection head or whatever task I'm trying to do, and that gives you the class or the logits of the classes, right? So what are the things that we need to understand right now is I can I can visualize my transformers like the ones used in NLPs into computer vision just by patchifying my entire image and linearly projecting them. And with the linear projection, once I add positional embeddings and I have this class token inside of it, I get one single class token or learned class token which goes into the MLP head. Now a little more due to the fact that I am getting some interactions from you all, could you also let me know what can be a possibility if I don't use this class embedding? What is one thing which I could do to omit this class embedding, but it would still give me one vector? Can you guys I'm open to taking wrong answers, but I really want you all to, uh, you know, interact with me so that it's easier for me to make you all understand. What is one thing? So I'm reforming my question. What is the one way that we can also do to omit this class embedding so that I get one vector at the end? It's a very simple question and it's a very simple answer if you all come to the answer. So I'll wait for a minute or two.
Are you trying to ask like something like a one-hot encoding, which will be one vector instead of multiple vectors representing a class?
No, what I'm saying is leave alone the MLP head. I'm not even interested about the MLP head. The main important thing that I'm interested in is the output just after the transformer encoder. And I really like how you said one hot encoding, which basically is a vector which you know does a discrete sampling, but I'm not interested in the classes. And yeah, you can go on. So what should be one thing which forms the same vector or a similar vector, one vector about which describes the entire image? So the previous thing was by a class learning embedding, which goes in, which learns, and I'm just going to neglect every other embedding and only the class embedding. But now I don't want to use the class embedding. What is the other alternative that I could do?
I didn't really understand the question here.
Okay. So the question is that, say in this diagram, the 1, 2, 3, 4, 5 until 9 are the representations of the patches, right? Now, once they go into the transformer encoder gives you another representation of 1, 2, 3, 4. It gives you a richer information about 1, 2, 3, 4 with global attention and all that stuff. So essentially, you would have outputs which comes out of the transformer encoder in the form of 1, 2, 3, 4, 5, 6, 7, 8, 9. And I think I should be drawing it out so that it's better understood. So if you have patches coming in, and there are 4 patches getting into a transformer encoder, what the transformer encoder should do is that it should give you representations of each patch individually. And this is patch 1, and this should be patch hat 1 because this is a different representation than this, right? Does that make sense? Now once you give a class embedding, CLS, once you give a class embedding, it should also give you a class embedding, like a class embedding which is different than the original class embedding. Does that make sense again?
Yeah.
Yep. So what I'm doing with my transformers, or what the Google brain did with transformers, is that they neglected everything other than this class embedding, because they found that class embedding kind of imbibes every other representation that it has. So I just need one vector which goes into my downstream task, and that's all. But what I'm saying is I don't need this class embedding. I'm just an arrogant prick who does not need a class embedding. I want everything to be done by these patches itself and the vectors from the patches. How am I going to get one single vector from every other patch?
You can concatenate them. So,
Absolutely, you can concatenate them. That's a very good answer. Something else?
and
Concat,
and you will have attention values also, right? So
right? Right.
you can do some kind of a multiplication and get some weighted concatenation out of it.
Yeah, so that's a very good answer. Now think about it. Inside the transformer encoder, am I not doing the same thing? I'm going to have attention weights. I'm going to have representations. I'm going to scale them. So these are already attended weights, like not weights. These are already attended representations. It's just a different representation which has all the attentions. But concatenation is a great answer. I'll take that as an answer. Another thing, something else on the terms of concatenation, think about merging. How do we merge? How do we represent everything together?
One way to do about is take a subspace and try to project all the vectors to the same subspace so that the dimension reduces, and
Yep.
then you
So
can
are you
concatenate that.
mhm. Right? So what basically happens is something called as a PCA or a TSNE, where we are trying to. Uh, the answer is that if you have a lot of vectors in an embedding dimension, say this is the embedding dimension that I have, which is an embedding dimension of 3, and you have a lot of vectors going in. You can project this embedding dimension to something else where all the vectors can be represented as one vector, right? Am I understanding this right, Yash?
Yeah, sort of.
Cool. So this is one. The most simple part of the answer that I was looking for, and it's not the correct answer, but something which researchers have picked up on, is using a global average pooling. So what they do is they global average pool everything, which is also very similar to what you have said in this answer, like having something like 3 vectors, and you global average pool and have one vector inside of it. So that was the answer I was looking for. But concatenation and PCR, TSNE, or embedding like the subspaces were brilliant answers. And what I would also want you all, or maybe Yash, to do is that if you ever go into vision transformers, please use your ideas. You go in. Don't use global average pooling. Don't use class embeddings. Use your own techniques. Maybe you'll have something which you can showcase to the world. So right after that, with the vision transformers, I come to the contents of this slide. So I really wanted you all to not see what my contents are before the slide began. I wanted to come to it so that I can have a back, like a series of things that I covered, so that we can all go back together and do it step by step. So the first thing was sequential data modeling. So we did MLP. We understood that sequential modeling is not possible with MLPs. And then we understood RNNs, LSTMs, but both of them had a representation bottleneck. That is the gradient of the backpropagating gradients when squished, right? Were squished, and we did not have proper gradients flowing. And then we moved on to attention. What attention did is that it attended, or it, with weights, with attention weights, it attended to parts of the sentence or parts of the images for that matter, which were required the most for the downstream task. And with attention, I did not write cross attention here because attention is a generic term, but self attention is not a generic term. It's something which you do on yourself. You do you apply the attention on the inputs itself, where the keys, queries, and values are from the inputs themselves. And once we understood how we did cross attention and self attention, we straight away went into transformers, and we kind of understood or intuitively made sense of how transformers work, how positional embeddings work, and then moved on to vision transformers, where we conveyed the entire knowledge base of whatever my slide decks had into the vision community. Uh, a little something from my end is credits. I really wanted to thank TFUG Hyderabad and Chennai for hosting me. I would like to also thank Ritvik, uh, who is, I think, inside the meet, who helped me with my slides. PyMed Search, where I work, to help me or let me do talks like this, even in a hectic schedule. Saik Paul, who is one of my mentors, who made some crucial, changes into the slide and asked me to use and not use some slides. Dave, who was one of my guinea pigs of the slides, so that's there. And Merv, who basically tied me to the community, that is TFUG Chennai and TFUG Hyderabad, to host or to be a speaker. And now we will move on to some questions.
Hi, Arit. I'm audible.
Yeah. Go ahead.
So, yeah, it was nice to learn about the vision transformers.
Mhm.
Have you used any GPUs
Yep.
to train the model using
Mhm.
the transformer which you mentioned?
Right. Yeah, I did.
Okay, which GPU you used?
A100s.
A100s. Oh, actually, I work as a R&D in the lead in Capgemini, and
Mhm.
I work in code generation using GPT-3 fine tuning,
Mhm.
GPT-J fine tuning.
Right.
Uh, so I like to connect with you separately because I'm getting error while I'm fine tuning GPT-J on A100s in
Mhm.
GCP.
Cool.
Can you help me with that?
Yeah, sure. If you would like to connect me over Twitter, I can take personal messages. Just as a matter of fact, I would like to have questions which are more related to the slide deck that I have provided, and with questions like these, I would like to take them personally in some social media or some other stuff. So yeah, Mohammed, you're welcome to connect with
Yeah,
me on
thank you.
over Twitter. Yep.
Yeah, it was a good present
Thank you so
demo.
much.
Yeah, thank you
Thank,
so much.
thank you so much.
Hey Aritra,
Hi, yes.
I joined in a bit late.
Mm-hmm.
Can I get the slide decks or maybe the recording?
Yep.
Or you could share the link somehow.
Yeah. I'll share the slide deck right after the talk, so you can follow me on Twitter to get the slide deck. And I'm also going to build the collab notebook because I promised doing the collab notebook for the softmax probability distribution. So it's going to take a little bit of time, but I'll surely publish the slide deck.
Sure, thanks. And also
Absolutely.
maybe if you are looking for collaboration on any work,
Mhm.
I'm good at PyTorch. I'm mostly
Cool.
from the NLP background.
Cool.
So I mean I'm open to it.
Absolutely. Thanks for letting me know.
What is your name? Who speak? No,
Oh, my name is Aritra Roy Gosthipaty.
no, the other guy who said he's good in NLP by
Oh,
touch.
Yeah, Yash.
Yes, okay, yes. We'll connect. I'll connect. I like to connect with you soon. Thank you.
Sure.
any other questions related to the slide deck?
Uh, I had some doubt on how you are, splitting the images into patches. I mean,
Mm-hmm.
do you have any? So, are you trying to do some kind of a convolution to split it, or how are you splitting it basically?
Okay,
Uh,
so I'll just share my screen real quick so that we're on the same page while I answer this, because uh, patchification is a really good thing. So let's go here because this is a GIF which would not make sense so much. So there are two ways to patchify. One is using einsum and reshaping. So you use tf.einsum or torch.einsum or whatever. Um, Einsum is short for Einstein summation, and it basically, reshapes or multiplies or does a lot of stuff to the images, and you patchify. So I'm not really interested in that because it takes a lot of time. The most important thing or the easiest way to do patchification is using convolutions. And how do you do it? You do it by using a kernel of 16 cross 16 because you're trying to do a patch of 16 cross 16, and you set the strides to 16. What happens then is that the convolutional kernel that goes into the image, like the top left or top right or whatever, however you are doing the convolution, it goes into the image and then it strides right after that whole scene. So it does not have an overlapping scenario. It has an unoverlapped or not overlapped scenario, and it tries to figure out the patches. Now, uh, think about it. what does convolutions do? A convolution is basically trying to project the images as well, right? It does not do just patchification. Now, if you want to have weights equal to 1, you can surely do image patchifications. But what I'm trying to suggest here is that the problem that we discussed with image patchification and vocabulary and vectorization is that you have patches and you also need to linearly project them. Why not with convolutions you do both? With convolutions, you're not only doing patches, you're not only going on patches, but also, with the convolutional kernel learning, you're also projecting them. So this entire thing happens in a single step, right? With convolutions. So that is what I understood, not from the paper, but from the code repository. And the official code repository from Google Brain is, I think, in JAX. So you're all free to go out there and see for yourselves how it basically happens. But that's really ingenious in my opinion. Like you're doing patches as well as projecting them just with convolutions. So yeah, I think that hopefully answers your question.
Yeah, it did. Thanks.
Cool.
Hi Aritra, thanks for the excellent presentation.
Hi Darshan. Thanks for letting me know. Yeah.
I just had a bit of a general doubt for transformers and CNNs. So basically, whenever you pick up a paper or you look into some research findings, how exactly do you go about, understanding it and trying to implement it? Because there's a lot of new concepts coming up all the time, right? So if you could provide a few tips on that aspect, that would be really helpful.
So thank you for this great question. So before answering this question, I would really want you all to know that the answer that I'm going to provide may or may not work for you. So it's not like a hard written commandment that you are going to follow and you are going to understand the paper. So what I do most of my times is that I started understanding attention very late because I was not fundamentally strong with RNNs, LSTMs, or sequential modeling. And if you go to my GitHub repository, like my GitHub profile, you will find one repo which is RNN Viz, and I think I'm going to share this out with you. So this is my GitHub profile. If you can go there and you'll find this one pinned repository called RNN Viz, which uses no framework like TensorFlow or PyTorch. It's written in pure NumPy code. And remember that we don't have auto differentiation in NumPy. So I had to write the backpropagation algorithm from scratch on a whiteboard on a piece of paper, and had to have like a grueling 1 month or 2 month experience, where I'm trying to figure out what this paper means. So right after that, you kind of like what happened to me is I kind of understood how the backpropagation works, how the forward feeding works, and then move on to something a little different or a little difficult. So if you don't understand the concept, don't just lose hope. You go back to the foundations, you try to implement it on your own, and coding is the best way of implementation of a paper. And not only coding from scratch, like I was very hard on myself when I tried to do it on NumPy, and I think that it's not really required. So what you could do is you could go to the repositories that the official document, like official repositories, you go to the code, you understand the code, talk to the authors if you would like to, because in every paper you get the mail of each and every individual author. And this is a big step. You would not be able to just implement a paper all of a sudden. You need to give yourself that time to understand, and everyone grows at their own pace, which is very beautiful. So you need to understand that you have to go back sometimes, and you have to go do this to and fro. So I'll share a little anecdote that I'm reading a paper called Group VIT, which got accepted at CVPR 2022, like that is this year, which is from NVIDIA. And when I started attention, or when I started RNNs, I used to look up to NVIDIA's code repositories for GANs, for style GANs and all that stuff. And I did not understand things. Like I did not understand how the code works and all that stuff. So it basically comes to a point where you are building on the foundations and standing on your foundations so that it's easier for you to understand a lot of concepts. And for that matter, I still don't understand a lot of concepts, and I somehow find shortcuts or maybe skip them. But yeah, so you have to find the sweet spot of your foundation so that you can build on top of it. So I think that answers.
Yep. It definitely helps a lot, Aritra, because typically what you would find in the job is like, somebody gives you a paper and they're like, hey, okay, this is the paper, implement it in 1 week. And you're like, oh, okay, wow.
Right. Absolutely, yeah. So you need to have that foundation. You need to give yourself that time to make sense of it. And if you have peers like I do, I have great peers. Like Ayush is one of my peer who is in the meet. Ritik is one of my peer who is in the meet. We collaborate on a lot of stuffs. We have Keras examples together. We talk, we do banters, and we also kind of get into an argument like my code is working, and I really get excited when somebody finds a problem in my code. So the peer review sessions with people of your community, or maybe if you go on to contribute to keras.io, you get a peer review from the one and only Frashwa Shole, who is also the creator of Keras, and you get to understand how he thinks, which is very important. You need to understand how people in the community think who are better than you, and it's no shame to come to a point that you understand there are going to be people better than you. So if you are okay with that, I think it's going to be growth end to end. So yeah.
True. I think that bouncing off ideas and discussions, it results in a lot of peer learning and a lot of growth in terms of understanding.
Absolutely.
True. Yeah. So thanks, Aritra. Thank you so much.
Absolutely. Thank you so much for the question. Anybody else with some questions?
ಯಾರು ಇದನ್ನ
I think that makes sense, Vijay, to conclude the session if you would like to.
So Aritra, you would be sharing the recording and the slides via Meetup, or how exactly?
I'm going to share the slides. I don't think the meetup was recorded. So I'm going to share my slide deck through Twitter. So my Twitter handle is, share this in the chat. So if you want to throw a follow, please do. And I'm going to also share the collab notebook with you all about the softmax and why we do the scaling term, that is the root over dk, so that it's easier for all of you to understand.
Okay.
Thank you, Ayush. Thank you for your kind words.
Thank you, Aritra. Thank you so much.
Yep. Thank you, Vijay. Absolutely. I would love to. Bye-bye.